I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
the podcast that helps you understand the chemistry of your everyday life. Bonus edition.
I almost cut Jam off to sing bonus edition. If you heard my little whispered, oh.
Yeah, before
lips. I forgot.
Before we even finish describing what the podcast is.
I just love it. Okay. So, what we're going to start out with this time is actually is a pretty funny one, I think.
Okay.
You can read it. I have it here at the top.
Okay.
It's a friend of ours has had the same argument with his coworker for 5 years.
Okay.
He literally said we've been at an impasse for 5 years. So here you go. This one's for you, Grant.
Okay, starting here.
Yeah, so right there.
Okay, so this is what Grant sent to us. This is his writing, basically? Is that what you said?
The first part is his writing, and then I summarized the argument.
Got it. Okay. So Grant sent us this. Pour coffee into an insulated mug with a lid. Seal it. Something I've done many times. Here I have my iced coffee, not hot coffee, but iced coffee in an insulated mug. Seal it. Open it a bit later, and it goes when you open it. The coffee burns your tongue so bad that you have to wonder if it got slightly hotter while sitting in the mug. Wait, could it have actually gotten hotter? So our friend who wrote this in, his coworker, we'll call him D, contend that because the coffee heats up the air, that then wouldn't the increase in the air's temperature heat up the coffee because they're right next to each other? And he also says maybe the air's temperature increases, which creates more pressure, and as pressure increases, temperature increases. And then they've been at this impasse for 5 years.
Yeah, he gave a really detailed breakdown of the conversation and then said this usually continues until one of us says, I really have to get back to work. So here's my thought. What?
It's just so funny because I've had conversations like that with Grant where it's like you keep going, but also it's funny in this case because it's like two people who I'm guessing, I think I've met this coworker before and of Grant's, his former coworker of Grant's, and they are both very curious people and analytical, but neither of them scientists. So then you have two people speculating, and they can't ever prove either of each other right or wrong, and so it would go on forever. And I think Grant and I've experienced that too. So it's just kind of funny to me.
Well, I actually agreed with everything Grant said, which he doesn't know that yet. He sent it to me, and I was like, "This is interesting," and asked a few questions and made a few comments, and then I told him, "Do you want to know, or do you want it to be a surprise?" And he said, I want it to be a surprise. But so he wrote out the conversation and everything the coworker said. Then I had the same argument that Grant had in my mind before I would read Grant's.
Okay.
So I pretty much agree with everything Grant says, but I have better reasons, I think, because of being a chemist. He just goes based off of intuition, and his coworker doesn't feel like intuition is a good enough reason. But in some ways, I think intuition is our observations about the material world.
Right.
And that is
educated guess about whipped cream.
Yes.
It's like it is intuited by the data I do have.
Yes.
Which is not nothing.
Right.
And so, any of us making guesses have something we're basing it on.
Yes. Right? Okay, so here's my thought. I think first to truly answer this question, we have to take it as a closed system. Does the coffee get hotter or not? So let's pour in our coffee and let's put on a lid that creates a perfect seal. Let's pretend like no heat will be lost or gained from the surroundings. And that is called an adiabatic system in physical chemistry. And my degree is not in physical chemistry, but I have taken 4 physical chemistry classes. So this is what I'm basing it off of, my physical chemistry knowledge.
Okay.
I could be right or wrong. But and if there are physical chemists who listen, hit us up if we're wrong. I think this could be an ongoing conversation.
Also, I have my own theory that I'm going to share afterward to not muddy the waters, but I'm going to try to capture it in my mind and not let it be affected by anything you're about to say.
Okay. So the first step for sure is true. The coffee has to heat up the air. And we talked about this in the episode where we talked about how thermoses work. Do you remember that?
I do remember this, yes.
And so kind of like we talked about, the reason things cool down is because if there's a concentrated amount of energy in one space, then that energy will naturally be distributed to the other molecules around.
Right.
So like if there's a whole room and the molecules are moving pretty slowly in that room, but then there's a hot cup of coffee, they would distribute the energy out. And that's why everything eventually would reach the same temperature.
Okay.
So in this case, though, we're in a closed system. So what would happen is if the air is colder than the coffee, enough energy would leave the coffee into the molecules in the air so that they roughly are even in energy.
Okay.
Okay, so we've got our closed system. It's a fixed volume and it's a fixed number of molecules.
Right.
Okay. So the first step is true. That's why, though, that coffee heats up the air.
Okay.
And it is also true that as coffee heats up the air, there will be increased pressure because we've talked about this before in the tire episode.
Yeah.
Molecules moving around more exert more pressure on their surroundings.
Right. Right.
So we're all agreeing that in our closed system, the coffee heats up the air.
Right.
Now, the next question is, then can that air go back and heat up the coffee? And I think he kind of has two separate arguments, and maybe he doesn't realize that, but in the flow of the conversation, I found two arguments. And the first one was, you read it, wouldn't the increase in the air's temperature heat up the coffee because they're right next to each other? And I don't think that's true because if the energy was trying to evenly distribute, it would evenly distribute and then stay there.
Right. It achieves an equilibrium kind of deal.
Yeah.
And then stays.
Yeah. I don't think it would be like, okay, so we're shoving air or shoving heat into the air and then that'll come back into the coffee or whatever.
Right.
Even if it did, if it took a while to get to the even amount, if there was like fluctuations in the temperature, I don't think it could heat past what it would have been to start. But then I think, so I think he said conduction, like that conduction won't heat back up the coffee higher than what the energy it already lost was.
Right.
I don't think that that's possible. Because even though there was some energy in the air molecules already, I don't think they'll put so much energy that they could overwhelm,
right.
Because
then it'd be almost like, could it pull so much heat out that it cools the air?
Exactly.
And then but yeah, otherwise you're asking, could there be more energy than there was to start with?
And I don't think there can be in this system. But then his other theory, and this is a closer reason I think it maybe could happen, but I still think it doesn't. Sorry, D. So his other theory is the air's temperature has increased, so pressure increases. And if pressure increases, if there's more pressure, then temperature has to increase too. But I think he's making sort of a fallacy here because in this case, the increase in pressure is caused by the increase in temperature.
Right.
Not the other way around. So he's right. If I were to exert more pressure on a system, so if we had our thermos and we made it smaller and smaller and smaller and smaller, it would heat up, and have more and more pressure until it exploded or couldn't get any smaller.
Yeah.
But in this case, we have a fixed system once we put the lid on. And yes, there is more temperature that causes the pressure in the air part to go up. But I don't think then that means that then it could increase the temperature. Because if it did, then it would have to increase the pressure again, and then it increase the temperature again, and then it would increase the pressure again. I think it stops at the temperature increases the pressure. Like the temperature causes the pressure to rise, but the pressure doesn't keep raising the temperature.
Right.
They go together and then they kind of stop is how I envision it.
Right.
Now, he could have thought, oh, well, the increase of pressure puts more pressure on the liquid too, and that increases the temperature of the liquid. However, the idea that as temperature increases, pressure increases is a gas law. So this is what's known as the ideal gas law. I think you probably did some PV equals nRT stuff.
Oh, sure. Yeah, I think that sounds familiar. I just don't remember it very well, but
it's like
yes.
PIV-NERT, whatever ideal gas. So they're like, in an ideal situation, a gas would act exactly like this, basically.
Right.
Well, molecules and gases aren't the same. So I don't think we can say, oh, well, it's increasing pressure on the liquid, so the liquid also is going to get hotter. Because liquids are already, the molecules are so close together. They're like held together, you know? They're like having intermolecular forces, they're like touching, you know?
Yeah.
So if you're pushing them closer and closer, they get closer and closer to a solid.
Right.
Well, water's a little different because it'll like expand once it rearranges when it freezes, but gases are different because they have tons of space between them. And then when you make that volume smaller or put more pressure on them, you know, in the smaller space, they're still able to move around in that space.
Right.
But liquid doesn't really behave that same way. So I don't think we can just uniformly slap on, oh, there's an increase of pressure in the air in this flask or thermos or whatever.
Yeah.
That pressure will be exerted onto the liquid, and the liquid will then also compress and therefore be hotter. I don't think that that's a path we can follow.
Right.
But even if it was a path we could follow, I still don't think the pressure would exert enough energy to get the coffee hot again.
Right.
Hotter. As hot as it has already lost, and then hotter still.
Yeah.
Is what they're saying. Could it have gotten hotter? So I still don't think that's possible.
Yeah.
So, yeah, for all those reasons, I guess I think that there is not a way that I could see that the coffee would have gotten hotter.
Right. And maybe there's a sensory sort of trickery there because the air is now hot also. And so as you're drinking it, there is a feeling that like there's just more hotness that you can feel even before you've taken a sip, you know? But yeah, the other thing that I've experienced in all my thermoses is like, I know you said this at the beginning, assume it's a closed system, but it's really not though, because this will get hot. It slowly does, and it's intentional, but I can tell a bit of the temperature of my coffee based on holding the thermos. Yeah. And it itself gets hot, which means some of the heat's being lost.
Yeah.
So.
And in really high quality, what kind of brand is that?
This is Hydro Flask.
That's a pretty good high quality thing. But even in like Yeti cups, I can't tell how my coffee is, but the lid is not perfectly sealed.
Right.
And I think that's the area of weakness in a lot of thermoses is like you're losing stuff from the lid. So if we're really talking in reality, if we're like not talking about a perfectly closed system, I really think it's impossible for the coffee to get hotter because I do think air is escaping. Yeah. And as, you know, those molecules are escaping, they're taking their energy with them. Yeah. You know.
And it doesn't get like, not a ton is leaking out in terms of heat, but I can tell when I have hot coffee or cold coffee in here because it'll at least be a little warm. Yeah. It never gets like hot to the touch or whatever. But like it makes sense if it's heating the air's touching metal, the metal wraps all the way out and around, it's going to happen. You're going to lose it somehow. So I think you have given Grant a lot of good scientific ammunition against his little coworker.
Yeah, Grant pretty much said everything I already said. He said it in different ways. Right. He said it more like a mechanical engineer. Is that what his degree is in, or is he a software engineer?
He does web development and software, but his degree is in, I think, the arts and technology one from.
Oh yeah.
Which is kind of
Well, he had a good understanding. Like he also argued against like, oh, that would be a perpetuating system kind of. And yeah, he had a very good understanding of the way that the molecules moved. And I agreed with all of his arguments actually. But I just was able to take it a step further and get to the molecular level and also draw that distinction between we can't always apply gas laws to liquids. And I think what the coworker thought is, this heat, I don't think he thought it was perpetually heating and heating pressure. I don't think he thought that. Yeah. I think he thought it was heating and it increased the pressure and then that pressure exerted on the coffee and then the coffee would had to get hotter because it had more pressure on it. But that would only be true if it was like a separate gas, I think. Right. I don't think putting pressure on the coffee would automatically make it for sure hotter. Yeah. Now, someone who studies the physical chemistry of liquids could probably answer that question better. But regardless, I don't think it could ever replace the amount of energy it had lost. So in that setting. So I think there's no way it could have gotten hotter.
Interesting. I love those kinds of questions and debates.
I know.
And what is cool about being two non-scientists in their case, but they both have opinions about stuff and care and think deep about how the world works, is that they can keep going back and forth like that for years.
I mean, I really had to think
that.
about it. We're doing a fitness competition right now. I think I mentioned it. And so we're supposed to seek 5 minutes of intentional sunshine. So I went outside for my 5-minute walk, and the whole walk, I was like, now let me think about that. Would putting pressure on the leg, like that was the thing I got stuck on. And I was like, I just don't think we can apply that. And then I went and looked it up to make sure, like, does this gas law apply to this? No, I don't think it does. You know?
Yeah.
But so even me, it kind of got me in a spiral. And then I spent like probably 45 minutes trying to figure out a way that I could explain it, that it made sense.
Yeah.
So it was fun. I liked that question a lot.
I liked it too. That was a ride for me. I love it.
Thanks, Grant. This one's for you. Sorry, D. Sorry, coworker.
Okay, moving on from Grant. Love you, Grant. XOXO. This is from our friend and Patreon supporter, Avishai. And Avishai said, I just finished listening to the latest Q&R episode.
This was when we speculated about yeast.
Yep.
And what they were.
Yeah. Yeast are fungi, which are eukaryotes. They have chitin. They have chitin in their cell walls. And they are heterotrophs, meaning they get their nutrition by absorbing molecules. Plants make sugars from CO2.
Okay, so I want to cut in here and make a distinction. Okay. Heterotrophs, I believe, eat their nutrients. Autotrophs make their nutrients. So I think what they're saying is the difference between plants, what Avishai is saying is the difference between plants and fungi, which I was like, what even are fungi? Is that plants are autotrophs and fungi are not.
Okay, got it. And he said they also have mitochondria and other organelles that bacteria don't have. So generally, yeast in food eat sugar and generate ethanol, which is lethal to bacteria. That's why Near East and European cultures put it in water to support civilization. That's interesting. Did not know
is that maybe like why so many cultures drank beer instead of just water?
Oh yeah, maybe so.
And I've even heard like in biblical times, wine then wasn't like as intense as wine now. It's just like fermented enough to keep the bacteria.
Right.
Kind of like kombucha, probably.
Yeah. And I guess you could travel with it easier and stuff like that too, or whatever. Yeah. And then he said, while bacteria eat sugar and make acids to kill yeast. So if your fermented food is sour, like pickles, bacteria. If it has ethanol, it's yeast.
I am confused about the pickles because I thought that was just in vinegar.
Right. Yeah.
But I don't know. But like kimchi, I think, is bacteria. So it's sour.
Right. I mean, and kombucha, you ferment it. And if you go too long, it gets real sour and vinegary.
Isn't kombucha yeast and bacteria?
It's both. Yep.
Okay. Well, he goes on to talk about sourdough, which also has both.
Yeah. In sourdough, you have both organisms living in symbiosis, which is probably similar to kombucha, having each kill the enemies of the other. Okay. The bacteria generates the sour flavor and the yeast, the ethanol and CO2 to help the bread rise.
Yeah.
I also read a theory that the high acid content of sour bread allows it to better retain its water content, protecting it from drying when left in the open.
Yeah, it is pretty like wet feeling.
Interesting. He just threw a bunch of awesome stuff.
Yeah, I read that and I was like, whoa, I did not fact check any of this. We trust Avishai, but I did want to clarify. We learned so much and I wanted to learn, so thanks.
Yeah.
So I wanted to clarify. Now I know the difference between plants and fungi, which are basically that plants make their own food and fungi need to take it in from another source. And, they reproduce differently, whatever, but that's like a big difference. That's why they're not plants. I've spent so much time being like, why are they not just plants? It's weird that they're immobile, though.
Yeah.
I wonder if there's other heterotrophs that are immobile, or if it's or is all fungi immobile? Can yeast move? We have so many questions.
Yeah, that's a good question. I mean, I guess when you say mobile, like mushrooms are the reproductive part of fungi.
That's true.
Under the ground.
And it does grow.
Yep.
And if you haven't, go listen to the From Tree to Shining Tree episode of Radiolab because it is wild about mushrooms.
Yeah, totally.
Or I guess fungi. So that's a big one. And then
I was going to say, it's cool that we have a listener and patron like Avishai.
Yeah.
Because if there's a question that rises like, what even is yeast or whatever? At yeast, we have someone like him.
No.
A fun guy like Avishai.
He said at yeast. Avishai, I'm sorry about that.
Yeah, a fun guy like Avishai who can
fun guy. He said a fun guy.
Speak into this stuff. So.
I hated it. Okay. Anyway, I thought that was really interesting and fun. And I love it when we're like, I don't know, does any of our listeners know? And then we have qualified scientists who do know. And it's for them as like, oh, I know that. I'll share the same way I feel when people ask a chemistry question.
Right.
I'm like, all of us scientists doing the work.
And it is so hard because of how many things connect. There's so many questions that will get asked, like we'll get a message on the website or whatever, that will definitely venture into many areas of science, including chemistry, where it's like, well, the chemistry part I know, but some of this gets into like biology or food chemistry or physics.
Which I did not pay close enough attention in biochemistry. Yeah. It's a big thing that I would take back if I could. But
it's all connected, especially when it comes to food. A lot of questions from you guys come about food, which makes sense.
Somebody did reach out to me that said that they were teaching a food science class and that I could maybe audit it.
That'd be so dope.
I was like, what? Is this real life? So that's exciting.
Here's another question. This is a question from, I'm sorry if I'm mispronouncing this, Mayumi. Mayumi asks, I have one question that's been in my head for a while now. Why, when we put a bowl of water covered in plastic wrap, the plastic expands while it's heating, but then it sinks into the bowl afterwards? I think it expands because the water's turning into vapor and taking more space, pushing the wrap sort of cover out. But when it cools down, why, instead of just going back to the original volume, the plastic is sucked into the bowl?
Okay, well, I'm wondering why are you heating a bowl with plastic wrap? Can you think of any reason?
I have done that too before I really thought about heating plastics. Huh. But I've done it for things like from reheating something that has like rice or whatever. It helps to trap
the liquid in. Okay.
Yeah, and kind of steam it again. I think I just
add water to it is what I'll do.
Yeah.
Okay, so here's the expanding thing. I think you had a good thought. I would also add that when you are heating up gas molecules, they move around more and they exert more pressure. So that pressure probably stretches out the plastic wrap.
Ah, right.
But so does the water vapor. I think that if more water reaching that vapor point is probably also adding to the trapped gas on top of the bowl. Mm-hmm. So I agree. Now, it's hard for me to visual it sinking back down. I think if it's sucked into the bowl tightly, I would imagine that it cools down below the temperature that it was originally at. And then it almost creates like an absence of space. Like they're moving around less, like a vacuum kind of.
Right.
Or if it's not like tightly sucked down, it could just have like stretched out. And when it relaxes back down, it's just the stretched out part is just sunken in a little bit.
Right.
Like it doesn't have the elasticity to go back to before it was stretched.
Yeah.
So I don't know. It's hard for me to visualize because I've never done this. Is it being actively like sucked in, or is it just like loosely sunken in?
I think in my experience, I think it really was loosely sunk in, but I think because it's so uniformly stretched in a dome, depending on your bowl, how much space you have in it, and when it sinks back down, it could almost look like it's like the shape might seem like has happened.
Because when it cools down, the molecules are moving around less, and so they are not taking up as much space, and some of that water vapor will cool back down and condense back down into liquid.
Yeah,
and so there's less volume of gas. And so I could very easily see it just like loosely sinking back down. Now, if you take it straight from the pot and put it in the fridge, I think it would actually suck it down.
Oh, yeah. Right.
Like make a little vacuum. So I think those are your two options.
Interesting.
That's a good question.
Yeah.
These are fun ones.
Yeah, they are. This next question is from Dr. Floyd. Dr. Floyd said, high school chemistry teacher here. I've been enjoying the podcast. It's got me thinking about revamping my chemistry course. That's awesome. I think taking a real-life approach would improve motivation and understanding of the importance of chemistry. The podcast has a great way of breaking down topics into simpler expectations. I was wondering if anyone has created a lesson plan and/or lab activities that go along with your episodes.
Okay, I have lots of thoughts on this. First of all, thanks. I'm glad you enjoyed the podcast, Dr. Floyd. So the idea of taking a real life approach to learning, quote unquote real life, there's two. There's something called system thinking, which is like thinking about chemistry in the context of all the other systems that exist in the world. But the other thing is called context-based learning. And that's the approach that we take here is we take a context and we're not trying to connect it to everything in the whole world. I mean, I think there's a little bit of that. But we take a context and we try to understand the chemistry within that context. And I'm guessing that there have been papers published about that. So I'm not guessing. There definitely have been. And I'm guessing that you have access to them. The Royal Society of Chemistry, they have a journal called Chemistry Education, Research, and Practice. It's a free resource. You just have to like make an account and you can get articles about chemistry education and all the work that's gone into context-based learning. Also, you can get information about, you can do the same thing on JChem Ed, but I think that's Journal of Chemical Education, and that's in the American Chemical Society, but I don't think it's free. I think you have to have access through your institution or if you're a member. And so that's one resource. Another resource is I have a link tree, and we've meant to put this on ours, but we haven't yet. We want to put it on our website, but I am slowly breaking down episode by episode which chemical concept is at play in the episode.
Right.
And I would love to go back and add keywords in our description so people could just search them, but that is way down the line.
Yeah.
But for right now, you can go to my link tree. So it's linktr.ee, linktr.ee/organic Melissa. Organic, like organic chemistry. And I have the beginnings of that list. It's just a Google Drive link right now. So it's not pretty and it's definitely not finished, but that could help you. And then we also did those chemistry at home experiments where that is some sort of like lab experiments that we talked about the underlying molecules. And I know people have done projects where their students had to make a podcast or where they explain a concept from a podcast or they make a video or something, related to our episodes. So people have done that, but I don't think there's any formal lesson plans. And we did also receive an email from somebody named Adam as well, who's also a high school chemistry teacher, which way to go. I get so excited when we hear from high school chemistry teachers because that's a really hard job.
Yeah.
And also shout out our friend Tim, chemistry podcast supporter and chemistry educator, officially has a job as a chemistry high school teacher.
Heck yeah.
Yay.
Congrats, Tim.
So, but he reached out asking a similar question about like which episodes, is there a way to filter them? So right now we don't have them. Hindsight's 2020. When we started this podcast, we had no idea the number of high school teachers that would, really educators in general, that would want to use the podcast in their classroom. So sorry that we don't have a better resource, but that's what we have now.
Yep.
Maybe one day this podcast can pay my salary and I'll be able to make resources like that all the time.
Yeah, especially going back through old ones and trying to update things or like add keywords like that.
It's hard.
You can understand how it's like we're in like the 160s in our episodes. It's a lot of stuff, a lot of work. And it's going back several years of stuff.
Yeah.
So anyway.
Now we're coming up on our 4-year anniversary.
Yeah.
Wild.
Crazy.
So those are good questions. Thanks, Adam. And thanks, Dr. Floyd, for the work that you do. And hopefully we have more resources for you at some point. Or maybe even, maybe we could hire an intern. That would be great.
Yeah. This next question is from Madeline. Madeline asks, what is the chemistry of plant variation? What is going on in the plant for it to invert?
Okay, I think it might have been supposed to be variegation.
Oh, okay.
I might have spelled that wrong on there. Or maybe not. I don't know. I think it's variegation. So variegation in plants is when it's like lighter in one part and darker in the other. So you have a plant right here for the people who are watching on YouTube. See how there's lighter spots on this plant? Like some yellow, some green?
Yes.
Okay, that's variegation. There's also like stripes. You've seen striped plants. Or even like There's like a marble pothos. If somebody's at home and you want to look it up, where they have like white spots, that is called variegation. And I don't know the chemistry behind it 100%, but here's my thought. Chlorophyll is what makes plants green.
Mm-hmm.
And often variegation increases when a plant is in bright light. So it's like if they are getting too much sun, they'll stop producing as much chlorophyll. And so that way they're not like overloading themselves in that area. And so there's less literal chlorophyll there. And so that's why it looks less green.
Got it.
So like if you have a variegated plant in bright light, it'll be more variegated. And if you have it in dim light, it will be less variegated. Because then it needs more chlorophyll to get enough energy to keep itself going. So that's my guess.
Interesting.
But that was a fun question. Maybe we'll do a whole episode about it.
I had never heard that word before, I don't think either. Variegated. This next one's from Isabel B. Isabel asks, what is your favorite chemistry class that you've taken? Undergrad or grad?
What's your favorite chemistry class that you've ever taken?
I've taken 2 only. One in high school and one in college. And it's hard to pick. I actually liked both of them a lot. I have more fond memories for the high school one. My teacher in high school, chemistry, Miss Pittard, she was super cool. One of my favorite teachers. I had a lot of great teachers though, so I'm spoiled in that way. But like, yeah, made it fun, and I probably didn't have the best attitude as like a punk high schooler and stuff. Yeah. But several things I remember, and then she was interested in it, and some of that's contagious, you know. There's several things that I never fully understood that I just wasn't that willing to probably like to like put more effort into it, like things like moles and significant figures and stuff like that. That I remember being like, yeah, this is the worst and I hate this. And so that stuff I had a bad attitude about. But there are a lot of things that Ms. Pittard did a good job just making really interesting. And I ended up my senior year being I had some spare periods in the day. And so I was her teacher's aide and got to help sort of catalog the chemicals in the storage area and stuff. I didn't get to like really handle them, but like got to like touch a, vial of mercury or whatever it was, and like make a log of how much there was of each thing and stuff like that. And like, I wouldn't have done that if Miss Pittard hadn't been cool and also made chemistry seem cool. Yeah. So fonder memories there, but my college chemistry class was also really cool too. Yeah. So, and Dr. Marshall.
And he knows Oliver Sacks.
I did not know that.
Right? There's a book that I think Oliver Sacks wrote, like Dr. Marshall was written in the...
No way.
I'm pretty sure.
I had no idea. That's awesome. Yeah. But Dr. Marshall was super cool. Also, contagious love for chemistry. Yeah. And that was a cool experience. So, hard to say. Those are my only 2. And they're both good ones.
This is really hard. I feel like people are going to be like appalled when they hear this, but some of my favorite classes in college, my favorite class in college was a history class and was not my chemistry class. Huh. Whoopsie. But
Melissa.
I know.
Oh my gosh.
But similarly, Miss Mullis, my high school teacher, was amazing. She is the reason I love chemistry, period. And she was an amazing teacher. And I just really, really, really enjoyed her class. We like did such cool things. Like we mirrored a test tube and we like hollowed out pennies. Like we did did you do that reaction?
I can't remember.
Some pennies have zinc in their center and others don't.
We definitely did a penny thing.
And you can file off the edges, and then that's enough space for like a reaction to happen to basically dissolve that. Yeah.
Right.
But it doesn't dissolve the copper on the outside. Right. And I got to hold fire. Like there was like bubbled propane or butane, bubbled butane in these bubbles, and then she lit it on fire. And so it was like in your hand, there was fire. She just did...
That's cool.
A lot of really exciting stuff. And I just don't know that any other class could ever be that good because they were all also harder because they were college and grad school classes. Yeah. So that was probably the most fun one. I really had fun teaching the class that you took. I taught the lab for it. Right. And it was kind of like chemistry demo lab.
Yeah.
So that was a fun class, chemistry for non-majors. I really liked that one.
Yeah.
That was in grad school. And then in college, I did have, and it was like advanced organic synthesis class. And we would make things like, and take several, lab periods to make them. And in that class, I made sparklers.
Nice.
And I made dye that we like tie-dyed clothes with.
Dang, that's cool.
So that was really fun. I think those are probably some of my favorite chemistry classes.
Yeah.
Yeah.
That's
There
cool.
was a time in grad school though where I guess I kind of want to share this in case other people are in the same place. There was a time in grad school I did not know if I liked chemistry because we were so in the weeds about everything and everything was so hard and I had undiagnosed ADHD and I was like, this isn't even fun. Like, why are we this zoomed in on this thing that doesn't even matter? Like, I really had gotten to that point. And my roommate was like, think about why you liked chemistry in the first place and kind of like helped me zoom back out. And she was like, so do you still think you don't like chemistry? And I was like, no, yes, I do like chemistry. I just don't like this area of being zoomed in, I think.
Right.
And what I'm doing now is the perfect combination where I get to, talk about chemistry and study how people learn chemistry, but I'm not spending all this time down kind of in the weeds of it.
Yeah.
But also doing this podcast helped me remember that I love chemistry because there have been times in my career where that was kind of early on in grad school where I was taking all these classes and everything was really detailed and it wasn't really fun. But then after I finished my master's degree, I'd kind of had a bad experience and I was just kind of burnt out. And I was like, do I even want to do this anymore? I don't know. I'll try this education thing. But that was when we started this podcast. It was like pretty soon after that. And it really helped me remember why I loved chemistry. And yeah, it was like, oh, this is why I'm doing what I'm doing,
Yeah.
So for those of you who are maybe in the same place right now, that don't feel too sad.
Yeah, that's good.
Well, we talked about that for longer than I expected.
This is the last question I think we have for this episode, but from Audrey. Audrey asks, what is your all-time favorite snack? Ooh. That's really hard.
I think it's not, I don't think this counts as a snack, but I think I'm going to use it because it's like the most consistent food in my whole life.
I think that's probably getting at what she's probably wanting.
Yeah.
Even if it's not technically.
This has gone through some like iterations in my life, but basically some kind of pasta and marinara sauce. So when I was, younger, it was Chef Boyardee ravioli. You can't eat that as a grown up. It really does not sit well with you. So I upgraded to, those tortellinis that are like cheese filled that they sell at the store and you just boil them.
Yes. Frozen or no?
I get the refrigerated kind, but they also have them frozen.
Got it. Okay.
And then now, because I have issues with my blood sugar, that's, some pasta is like very blood sugar spiking. So now I kind of have to this is a little bit sadder, but I have lentil penne pasta and put cheese on top of it and put it in the broiler so it gets that nice browning.
Nice.
But my whole life, like a comfort food, like if I just don't know what to eat or if I don't know, like pasta with red sauce never sounds bad to me. Never. It never sounds bad. I can always eat that and it always feels safe.
Yeah.
So.
Dang, that sounds really good. I could definitely go for some right now.
Yeah, now I have to, sadly it's had to evolve, It's like my nutrition has gotten more demanding, but that's one.
Have you ever tried, there's this pasta, dang it. I think it's called tortellini.
Oh my God.
Really good. You have to try it.
I will say when people are like, what's your name? I'm like, Collini. It's like tortellini, but with a C instead of a T, which that's not exactly right because there's L's and R, but
it helps them get in the right phonetical
they get
area.
in the right mindset. It's like Olini. Oh, okay.
Yeah.
I know what Olinis are.
Yeah. Yeah.
So that's probably mine. What's
Tortellini,
yours?
Mussolini, just several
Mussolini. Oh no, I never
Just
thought
kidding.
of that.
Just kidding.
My sister said when she crossed the Italian border to visit Italy, they started speaking to her in Italian when they saw her last name, and she was like, "No.
Yeah.
It's much more common in Italy, and even at the American Chemical Society, I typed in my last name, expecting to only find myself, and there was an Italian chemist there whose name was also Collini, and I was like, this has never happened. Anyway, so that was shocking.
That's crazy.
Okay,
so I like snacks a lot. I specifically like more savory snacks. It's my Achilles heel or whatever you want to say. So I love things like Flamin' Hot Cheetos. Spicy snacks are kind of my deal. So jalapeno chips, Flamin' Hot Cheetos. There's
jalapeno chips.
There's a spicy Cheez-Its.
Yeah.
So salsa verde Doritos, whatever the spicy nacho Doritos are.
Those spicy nacho Doritos are good. But also, have you tried the Tapatio Doritos? Rhett and Link say those are the best.
I have not tried those, but I will have to. Salsa verde used to be a lot more common. You can still find them, but they're just not nearly as not every supermarket has them or whatever. Those are really good. They're not that spicy. But there's a flavor that's like,
I tried those recently, also because of Rhett and Link. And it was too close to Cool Ranch, in my opinion. And I had a bad experience eating Cool Ranch chips when I was younger. So it was like a little too. Yeah,
there's a little bit of Cool Ranch in there. I don't like Cool Ranch very much. To me, they're very overrated. But the iteration that happens with the salsa verde is like, I'm in for it. But those are some of my faves. And basically, if it's crunchy, spicy, I'm kind of there.
What about hot fries?
I haven't had those very much, partly because they just sound unappetizing to me. The hot part sounds good. I'm like, why? Fries are bad when they're not fresh. So why do I want fries that are in a bag?
Yeah, I'm unclear on how they're different than Cheetos.
Yeah.
They seem the same.
Maybe they're not actually really fries, and that might help.
They're not. They're like chips.
Okay. Maybe you should try them. The Takis are like the kind of rolled.
Oh, yeah, Takis.
Those are good too. I've had those and the Trader Joe's version. Very good. So, yeah, crunchy, spicy.
Mason loves hot fries, and I kind of make fun of him because I'm like, are you 12? And his cousin also made fun of him with me. She's like, he still eats those because she grew up with him.
Yeah.
And then right after that, I was on TikTok, and there's a Lizzo video, and Mason was like near me when I was watching it, and he goes, she's eating hot fries. Lizzo eats hot fries. And I was like, dang it. I can't make fun of him anymore. Yeah,
he's like, either you want to diss Lizzo or you want to admit that adults eat these too.
Yeah. So Lizzo eats hot fries, whatever.
That's very funny.
So you would probably like them. They very much are like Cheetos, only square, I think.
Okay, interesting.
Maybe it's like the shape is why they're called fries.
Yeah, I think that to me, if they just called them something else, I would have been more down. But I just
so should I get you a bag of hot fries and like put duct tape over it and write sticks, hot sticks?
Maybe so. Or like hot potato sticks or something like that.
Hot potato sticks.
Because like potato sticks, different story. It's basically like ruffles that are crumbled apart or whatever.
Yeah.
But yeah, the fry idea, because like nothing's worse than fries that have been anything longer than like freshly made just now.
Yeah.
Like fries 20 minutes after they're made are the worst thing in the world.
Yeah, I thought that In-N-Out fries were bad, but actually it's just that you had to eat them literally immediately.
Or get them extra well done.
I don't like extra crispy fries.
Ooh, I do.
Ooh, okay. Well, on that disagreeable note, so last month when we did our Q&A, we had talked about that there was a negative review. But while Jam and I were talking about that, we realized like there are also so many positive reviews, and a podcast that I really like will read some of their positive reviews and shout out those listeners. And I decided that I wanted to do that too because it's fun.
Yeah.
So we're going to add this on. We'll do more this week than we probably will in the future, or this month than we probably will in the future. But we just want to share some happy reviews.
Yeah.
Do you want to start?
Positivity, put some positive vibes out there.
Yeah.
And thank these listeners for their encouragement, because that's really helpful for us. So
yeah,
when we do see these or read them and or get notes from people that are encouraging, it's so helpful. So we're going to read a few. I'll read this first one from Jackie D. Jackie said, "Hello. I was just listening to your episode, Is Glass a Liquid, yesterday on my way home from my internship. And today I'm reviewing lecture slides as I prepare to go back to classes next week. And the first lecture in my Fundamentals of Materials class is about crystalline and amorphous materials. Making these connections is one of my favorite parts about listening to your podcast. Smiley face test tube.
Yay. I love that one.
You read the next one?
Yes. This is on Apple Podcast Review. The last one I think was a message on on Instagram. This one's a podcast review on Apple Podcasts. It's from user JG128534. They said, a great duo. They make chemistry fun. Just like the best educational podcasts out there, there's some conversation that is unrelated to the topic, but that's what makes it relatable. If they didn't, then it's just a lecture. That's so true. Keep it up, guys. And then they said, thanks for sharing your knowledge. P.S. Having Jim explain things back to you has made me a better trainer at work and oddly helped me in my marriage by doing that with my wife in important conversations.
Nice. That is a good idea.
Yes, I told someone I was in a group of people and somebody said something and I guess I kind of repeated back to them what they said, like, oh, so this happened. And one of the other people in the group was a counselor. And she said that's a counseling technique, that saying back or making sure the other person understands what you said is important in communication. So that's a good idea.
Yeah. This next one is from a user named A. Illig. I think that's right.
Yeah, I think so.
I absolutely love this podcast. Melissa and Jam make chemistry fun, as it should be. I binge listen to this podcast while working from home and genuinely feel like I've learned more about the world around me as a result. You can tell that Melissa puts careful preparation into her content, and she has a way of communicating difficult concepts in a way that's easy to comprehend, which is hard to do without visual aids, especially with chemistry. And the dynamic with Jam is very fun. He makes the show so light and fun and is a relatable layperson for Melissa to bounce ideas off of. I don't know these hosts personally, but at this point, I feel like I do, and I have so much respect for them. This show is perfect for those who love science and those who don't.
That's so sweet.
Yeah,
I was getting
really
a little
sweet.
teary when they were saying that. Also, I have work from home too, so we can pretend like we're working from home together.
Yeah. And we hope that's the case. Like, we want to feel relatable. That's why we like do the share about our weeks at the end and stuff. And some people might not want that, which is totally fine. But for those who do and want some kind of like, you know, levity and just whatever fun convo stuff mixed in with their science, and that we hope that that's something that some people want.
Yeah. And that's part of why we do the bonus episodes that are longer and more casual. It's like, oh, then you get to know us.
Yeah.
The last one we'll read is from user, I'm going to say it's probably Ender, N-E, like the Ender dragon in Minecraft. I don't know. Maybe not. It could be like Indrani or I don't know.
I have no idea.
They said, I love the well-delivered conversation but informative style of this podcast. A must-listen for anyone interested in chemistry like me or anyone curious about the world, also me. Keep up the good work. That's so sweet.
That's very sweet.
So, yeah, we want to highlight and lift up the people who support us, as well as, you know, sometimes we get those negative reviews, but these really keep us going, and we really do. When we get messages and emails, we read every one, and they mean a lot to us. There have been times where we've wondered, like, are we doing anything? Are we making a difference? Is it worth it to keep putting our time into this podcast? You know, it really is hours out of our lives, away from our families, away from our jobs. And consistently we've come back with yes, because we know the impact that it has on people because our listeners reach out. So thank you all so much for doing that.
Yeah, sharing this isn't to pump ourselves up at all in the sense of like, hey, everyone, look how good we're doing. But but just to show, one, we want to shout out people who send us in stuff and kind comments and stuff like that. And just the involvement of you guys is the best. And then also to just thank you for the encouragement. Because like Melissa said, it keeps us going, keeps us feeling like what we're doing. This is a thing we can do. This thing we can fit into our weeks. We know how to do this and juggle the rest of our lives. And this is the kind of show we can produce with the time and money we have right now. And to know that that is actually, even as it is now, is helpful and useful to some of you guys is really cool. So thank y'all for telling us that. And if you have a question like we go through in these episodes or an idea or whatever, we love hearing those from you guys. And you can reach out to us on our website at chemforyourlife.com. That's chem, FORyourlife.com to share your thoughts, ideas, and questions. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to patreon.com/chemforyourlife or tap the link in our show notes or the description to join our super cool community of patrons. If you're not able to do that, you can still help us by subscribing in our favorite podcast app and rating and writing a review on Apple Podcasts or subscribing on YouTube, because that also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson, and Jam Robinson is our producer. This episode was made possible by our financial supporters over on Patreon, and it means so much to us that you want to help make chemistry accessible to even more people, and that you support us financially, but also emotionally and mentally, that we should keep going. Those supporters are Avishai B., Bri M., Brian K., Chris and Claire S., Chelsea B., Derek L., Emerson W., Hunter R., Jacob T., Kristina G., Lynn S., Melissa P., Nicole C., Stephen B., Shadow, Suzanne S., Timothy P., Venus R. Thanks again for everything that y'all do to make Chemistry for Your Life happen.
Yay, chemistry!
Yay, chemistry!